Section: Introduction. In this section, we discuss the introduction of our work. Supervised fine-tuning, SFT, has been the traditional method for training large language models, LLMs, and GUI agents. However, SFT requires large, high-quality labeled datasets, which can lead to long training times and high costs. Additionally, existing open-source VLM-based GUI agents trained with SFT often struggle in out-of-domain scenarios, limiting their real-world effectiveness. Recently, we have seen the rise of rule-based reinforcement learning, RL, or reinforcement fine-tuning, RFT, as a more efficient alternative to SFT. This approach allows us to fine-tune models using only a small number of samples, focusing on specific tasks without the need for expensive human annotations. For instance, DeepSeek-R1 has shown how rule-based RL can effectively solve mathematical problems by assessing the correctness of solutions. Other studies have adapted this method for multimodal models, achieving improvements in tasks like image grounding and object detection. By concentrating on measurable goals, rule-based RL offers practical optimization for both text and multimodal tasks, providing benefits in efficiency and scalability while reducing the need for large datasets. Previous research in traditional vision tasks has relied on the intersection over union (IOU) metric for grounding and detection. In our work, we extend the rule-based RL approach to GUI action prediction tasks based on low-level instructions. To do this, our model generates multiple responses that include reasoning tokens and final answers for each input. We then evaluate these responses using a proposed reward function that updates the model through policy optimization methods like GRPO. Our reward function includes three components. 1. The action type reward, which checks if the predicted action matches the ground truth. 2. The action argument reward, which assesses if predicted coordinates are within the correct area. And 3. The format reward, which ensures the model provides both reasoning and the final answer. This flexible reward system aligns well with GUI tasks, ensuring accuracy and interpretability. For data preparation, we selected just over 130 training samples based on difficulty, diversity, and quality, making our method highly data efficient. Our experiments show that UI-R1 significantly improves performance on out-of-domain data, including desktop and web entries, highlighting the potential of rule-based RL for complex GUI tasks across various domains. In summary, we introduce UI-R1, which enhances MLLM's reasoning for GUI action prediction through DeepSeek-R1 style reinforcement learning. We create a unified rule-based action reward function that aligns with common GUI objectives and utilize a three-stage data selection method to gather high-quality training data. Despite the limited dataset, our model achieves notable performance improvements on out-of-domain benchmarks, demonstrating its adaptability and generalization in GUI tasks. Next, we review related work. Starting with Cog Agent, researchers have applied MLLMs to various GUI tasks, including device control and task completion. Some projects, like the App Agent and Mobile Agent series, use generalist models like GPT for planning and prediction, relying on prompt engineering and multi-agent collaboration. Others focus on fine-tuning smaller open-source MLLMs on specific GUI datasets to create specialized agents. For example, some enhance agents by adding functionalities for Android GUI elements, while others develop models for precise GUI element localization. Moving beyond task-specific fine-tuning, UI-TARs combine GUI pre-training with reasoning fine-tuning to better align models with GUI interactions. Despite their differences, these agents all depend on the SFT paradigm, which requires large, high-quality labeled datasets. Rule-based reinforcement learning has emerged as an efficient alternative to traditional training methods, using predefined reward functions to guide model behavior. DeepSeek-R1 introduced this approach, focusing on whether an LLM's final answer matches the correct one for math problems. This method allows the model to learn the reasoning process independently. Subsequent studies have adapted this paradigm for multimodal models, creating task-specific rewards for visual tasks, demonstrating the versatility of rule-based RL across various applications. By focusing on specific objectives without needing extensive labeled datasets, rule-based RL shows promise as a scalable and effective training method for diverse tasks. Section Summary. In this section, we discuss the limitations of supervised fine-tuning, SFT, for large language models and introduce rule-based reinforcement learning, RL, as a more efficient alternative that requires fewer labeled samples and reduces training costs. We present our model, UI-R1, which enhances GUI action prediction through a novel reward function and demonstrates significant performance improvements on out-of-domain data, showcasing its adaptability across various GUI-related tasks. Section Method. In this section, we describe our UI-R1 reinforcement learning training approach, which aims to improve a GUI agent's ability to carry out low-level tasks. We define low-level instructions as specific actions directed by a single state, like a screenshot of a GUI. For instance, click the menu icon in the top left corner is a low-level instruction, while create an event for 2 p.m. tomorrow is a high-level instruction. We will detail our training data selection and reward function design in the following sections, and we will illustrate the main components of our framework. We note that many rule-based reinforcement learning methods use the Group Relative Policy Optimization (GRPO) algorithm. GRPO serves as an alternative to the more common Proximal Policy Optimization (PPO) by not requiring a critic model. Instead, GRPO evaluates a group of potential responses to assess their relative quality. For a given task, the model generates several possible responses, and each response is assessed by executing the corresponding actions and calculating their rewards. Unlike PPO, which uses a single reward signal and a critic to estimate value, GRPO normalizes these rewards to determine the relative advantage of each response. The relative quality of a response is calculated using the mean and standard deviation of the rewards, allowing for better comparison among responses. Additionally, we ensure stable learning by minimizing the difference between the updated and reference models. We introduce a rule-based reward function that evaluates whether the model's predictions match the correct answers. This method aligns well with preference alignment algorithms and provides clear optimization signals. For tasks related to vision, other works have developed task-specific rewards. For example, in image grounding tasks, the reward is based on the intersection over union between predicted and actual bounding boxes. In GUI tasks, it is crucial for agents to understand where to perform actions on a GUI screenshot. To fill this gap, we propose a reward function specifically for GUI tasks, which includes two components, the action type and the click coordinates. Our action space includes various actions like click, scroll, back, open_app, and input_text, reflecting common scenarios in daily applications. The action type reward is calculated by comparing the predicted action type with the actual one, giving a reward of 1 for a correct prediction and 0 otherwise. We have observed that the most frequent errors occur in predicting coordinates for click actions. To tackle this, we designed a coordinate accuracy reward, where the model outputs coordinates indicating where to click. This reward is calculated based on the predicted coordinates and the actual bounding box. Unlike typical visual grounding tasks, our method emphasizes accurate action coordinate prediction, which is more relevant for GUI agents. We also use a format reward during training to help the model generate structured reasoning and final answers. Our experiments show that agents that produce reasoning processes perform better than those that only output action predictions. The format reward ensures that the model's outputs adhere to a specific HTML tag format, enhancing clarity and consistency in predictions. In summary, we emphasize the importance of structured outputs and accurate predictions in our training approach for GUI agents. Section Summary. In this section, we present the UI-R1 reinforcement learning paradigm, which enhances a GUI agent's ability to execute low-level instructions by employing the Group Relative Policy Optimization (GRPO) algorithm for training. We also introduce a tailored reward function for GUI tasks that evaluates action type and coordinate accuracy, ensuring that agents perform correct actions based on specific GUI interactions. Section: Training Data Selection. In this section, we describe our training data selection process. We find that rule-based reinforcement learning, RL, can achieve similar or better results than supervised fine-tuning, SFT, on math and vision tasks with fewer training samples. Inspired by this efficiency, we implement a three-stage data selection process to improve open-source GUI datasets based on three principles: quality, difficulty, and diversity. For quality, we start with the mobile subset of ScreenSpot, which has clear and well-aligned annotations for click actions. We also randomly select 1,000 episodes from ANDROIDCONTROL for other actions, but we exclude click actions due to misaligned annotations. For difficulty, we label samples as hard if the model's output does not match the correct answer. We keep only these hard samples in our dataset. For diversity, we choose samples with various action types from ANDROIDCONTROL, like scroll and input text, and different element types from ScreenSpot, such as icon and text. We exclude rare actions like wait and long press. After applying these criteria, we create a high-quality mobile training dataset with 136 samples. Next, we evaluate the grounding capability of our model, UI-R1, using two benchmarks, ScreenSpot and ScreenSpot Pro. ScreenSpot assesses GUI grounding across different platforms, while ScreenSpot Pro focuses on high-resolution tasks across various applications and industries. We train the Qwen 2.5-VL3B model on our selected data using rule-based RL and refer to it as UI-R1 to 3B. We also train a base model on the entire ScreenSpot mobile set, calling it Qwen 2.5-VL3B. For evaluation, we consider an action prediction correct if the predicted click coordinate is within the ground truth bounding box. We calculate accuracy as the ratio of correct predictions to total test samples. Our results show that our method significantly enhances the GUI grounding capability of the 3B model, outperforming most 7B models and achieving results comparable to state-of-the-art models trained on larger datasets. We also note that while SFT can improve performance with limited data, it struggles in out-of-distribution scenarios due to its reliance on specific labeled data. In contrast, our RL approach improves generalization and requires fewer training samples, making it a more efficient alternative. Finally, we assess our model's ability to predict single-step actions based on low-level instructions from ANDROIDCONTROL. We evaluate action prediction accuracy by comparing predicted action types to ground truth types and measuring the accuracy of click action predictions. Since ground truth bounding boxes are not always available, we determine correctness based on the distance between predicted and actual coordinates, considering a prediction correct if it is within 14% of the screen size from the ground truth. Section Summary. In this section, we describe our three-stage data selection process for refining GUI-related datasets based on quality, difficulty, and diversity, resulting in a high-quality mobile training dataset of 136 samples. Our approach, utilizing rule-based reinforcement learning, significantly enhances the GUI grounding capability of our model, UI-R1 3B, outperforming many larger models while demonstrating improved out-of-distribution generalization compared to traditional supervised fine-tuning methods. Section: Analysis. In this section, we analyze the performance of our UI-R1 model compared to the Qwen 2.5-VL/ZS model, highlighting the advantages of our reinforcement learning training framework. We observe that UI-R1 enhances action type prediction accuracy by 15% and click element grounding accuracy by 20%, using only 136 training data points. Our results show that UI-R1 performs exceptionally well even with limited training data, achieving better accuracy and grounding than larger models. This demonstrates the effectiveness of our approach in utilizing small datasets for significant performance improvements, making it a promising method for training in resource-limited settings. Next, we explore the relationship between the size of the training data and model performance. We compare two data selection methods, random selection and a difficulty-based selection, where we choose the top K tasks that the Qwen 2.5-VL3B model struggles with. We find that as the training data size increases, model performance improves, but the gains start to level off. Notably, our difficulty-based selection method outperforms random selection significantly. We also examine how reasoning length affects accuracy. Our findings indicate that as the reasoning length increases, accuracy tends to decrease, suggesting that the questions become more challenging. However, with reinforcement learning, UI-R1 shows marked improvements in reasoning ability, particularly on tougher questions. The design of the reward function is crucial for the model's self-learning. We assess the importance of two components in our reward function, action and coordinate rewards. The action reward boosts action prediction accuracy, while the coordinate reward enhances click element grounding. We compare this to an alternative reward design that uses an IOU-based reward instead of the coordinate reward. Our ablation studies reveal that the coordinate reward is more effective for improving grounding. However, we note that the action reward does not always benefit grounding tasks, likely due to the complexity introduced by a larger action space. This emphasizes the need to balance reward components based on task objectives. Lastly, we investigate the impact of different data selection methods. Our comparison of three methods across various domains shows that neither random selection nor using the entire dataset achieves the effectiveness of our three-stage data selection pipeline. This indicates that utilizing a smaller set of high-quality data can enhance performance.